Right, now that we've seen closed systems, we need to go to open systems. And what you're going to see predominantly in this class is steady state open systems. We're not going to make it super complicated by not making it steady state, right? So open systems are going to get us closer to the real world, but we're also not going to look at non-steady state systems because those are very hard to model. That takes a lot of advanced mathematics. So we're going to stick with steady state systems, okay? So the first law of thermodynamics for an open system at steady state is going to say that input equals output, right? If it's steady state, we don't have accumulation, and we're not going to have generation and consumption in this particular type of balance. So the input to the system is going to be the total rate of what we call energy transport in terms of kinetic energy, potential energy, work, internal energy, and heat into the system. And then output is going to be the total rate of energy transport, including all those 5 terms again, but out of the system. So this is actually going to take a little bit of deriving on the next couple slides, and I like to walk you through the derivation because I think it helps me make a little bit more sense of what's going on in the system. So we're going to see all 5 of these terms come up in the next couple slides. So let's start with the open system balance. We are going to define a term E sub j, and all j means is that it's the jth term of the jth input or output. We're going to have many inputs and outputs. So j is representing those numbers that we put on our flow diagram, 1, 2, 3, 4. And we're going to sum all those up when we're looking at inputs, and we're going to sum all those up when we look at outputs. So that's all that means here. And basically what our open system balance says is it says the amount of energy that comes into the system in terms of heat or work. We're also going to tack on any energy that's coming into the system in terms of kinetic, potential, or internal energy. And then that must be equal to whatever energy leaves the system in terms of kinetic, potential, or internal energy. So we're going to start with this generalized form, and then we're going to build from here how we get all the terms into this balance. So the first thing that we can do is rearrange, and we can say, well, the sum of everything out minus the sum of everything in has to equal the flow rate related to heat and the flow rate related to work. So you'll notice all these terms have dots over them right now. So we're talking in terms of flow rates on this particular derivation. So once we know and we rearrange this way, we know that that E sub j term is composed of 3 things. It's composed of internal energy, kinetic energy, and potential energy in the system. And we know how to define all those more or less in the system. So what we're going to do is we're going to start to add what each of those different things is to this overall equation that we have. So, for example, we know that we can say the flow rate of internal energy has to be equal to the mass flow rate times the specific internal energy of the system. It's going to be much easier for us to find the mass flow rate or the specific internal energy rather than the flow. So many times we're going to substitute this in for internal energy. We know that kinetic energy is equal to 1/2 m dot v squared for the system that are accelerating. So there's another m term that's starting to look like a theme, having a mass. And then if we look at potential, we've got a mass flow times the gravitational constant times that change in position relative to a specific reference point. So let's plug all of that in and see what we get for E sub j. Okay, so now E sub j, every single term has an m dot in it. So we factor that m dot out, and we say m dot times the internal specific energy of the system plus 1/2 v squared plus gz is going to represent the total energy that's related to internal, kinetic, and potential in the system. From there, we also know that our flow work terms are going to be related to the pressure and the volumetric flow in systems. So we know that the work flow in the system is going to be the sum of the pressures times the volumetric flow rate in minus the sum of the pressures times the volumetric flow rate out in the system. So what we're doing here on this slide is we're slowly building up from this very simple form of the total rate, how we actually start to calculate things by adding these individual terms here and by starting to specify what each of the terms are. So then from there, well, we know that the work total has to be flow work and shaft work in the system. So our total worked term that goes into the system has our shaft work plus our flow work, which is the change in what comes in minus what comes out. And what you'll notice here is that I've changed it from a volumetric flow rate to a specific volume times a mass flow rate. And that's 100% okay to do as long as we're being consistent and staying in the mass form of this particular equation. Then, if we put everything all together, what we see is that we've got Q plus W equals the change in what comes in. So we take the mass flow rate times all of these different terms. Oh, look, there's a mass flow rate that could get pulled out of this. So we add a work term over here. And then we have everything that comes out of the system as well. So this is getting complicated really fast, but all of these different symbols that you see here, right, all these different variables, these are things you can calculate. Whereas what we started with is not something you can calculate. So if we move on from there, we know U with the hat over it plus pressure times V with the hat over it equals specific enthalpy. So what this is going to do is this is going to allow us to take all of this craziness and simplify it to this form right here, where we have a change in enthalpy flow is equal to kinetic plus change in potential plus Q plus W. There should be a plus right here associated with this H. So make sure that that's changed in your notes. I'll draw on the screen a little bit. There we go. That should be a plus for us. There we go. So that we have everything where it needs to be, because they all need to be on the same side of the equation. So that is the generalized form of your open system balance. When we need to plug things in, this is the form that allows us to solve for everything in the system. So these terms right here are related to H. This is related to kinetic energy. This is related to potential energy in the system. All right, so what I want you to do now is, knowing all the rules for closed balances and now knowing what we've got in terms of an open system balance, I want you to pause the slides and I want you to think about how you could simplify the steady state open system balance in each of these cases. So there's going to be a scenario here, and basically the idea is that we want to cancel a term out to make our open system balance easier. So take a pause and write down what you think you can cancel in each of these cases. So hopefully you took that pause, right? And if we look at A, there are no moving parts in the system. Well, if there's no moving parts in the system, we don't have any work in the system. So in that case, we can cancel out at least the shaft work component. We might not be able to cancel out the fluid component, but we can definitely cancel out the shaft work component. If the system and its surroundings are at the same temperature, that's an adiabatic process. It's the same as when we did closed systems. That means Q is going to equal 0. So if we know that the system and its surroundings are at the same temperature, we're good to go. If the linear velocities of the stream are all the same, that means that we can cancel out our E sub k, because we're not changing our velocity, which means we're not accelerating in the system. And then if all of the streams enter and leave the process at a single height, so there's no change in height within those specific unit processes, then we can cancel out potential energy. So a lot of times what we're doing here is we're taking basically a different form of the general balance equation, and we're canceling out terms that we can to help us as we go forward. So last thing that I'm going to mention here is, how do we do our energy balance procedures? So very similar to a mass balance, we need to draw something. It might not be a flow chart, it might be more of a diagram for ourselves. And then we need to consider the boundaries. That's going to be important. So what is the system and what is not? And we'll talk about this extensively in class. Then the other thing that we need to try and do is we need to check phases. If things are in the gas, solid, or liquid phases, because that's going to start to matter to us. And we also need to see whether or not the pressure and the temperature of the system are available. If pressure and temperature are available, many times we can look up things like specific heats or a specific enthalpy in tables, and we'll talk about how to use those in class. So generally we start out the same way that we have been for mass balances, but finding some of the values is sometimes a little bit tricky because we need to reference other tables or other concepts that we know. So that's where I'm going to leave you in this particular lecture. Make sure that you have all your equations written down so that you can start to apply this in our examples coming up.